Welcome to the lecture series in computer science. As a part of this series, this is a course on artificial intelligence and we are in unit 2 module 11. Specifically today we will be seeing a continuation of the last time's constraint satisfaction problem, where we will be looking at two algorithms basically. One would be the forward checking with the backtracking. If you see the constraint satisfaction problem, last time we saw the formulation overview, which is here, and today we will be looking at the backtracking portion as well as the forward checking with one of the algorithms like minimum heuristic value, and the other one would be the AC3 algorithm. This is towards the constraint propagation method. Now, this is an overview of the last time's session, where for CSP, which is a constraint satisfaction problem, the variables are declared, which is would be in x capital X with x1, x2 up to xn, and with the domain d1, d2 up to dn, and the constraints which refers to the scope and REL, which is a relation that deals with the value from domain assigned to the x values. So, if we see for this example with the which is the map of Australia, which we saw last time, the variables are WA, which refers to Western Australia, NT Northern Territory, South Australia SA, NSW is New South Wales, Queensland and Victoria. These belong to the variables x, and the domains that we refer, this domains is going to be the three colors red, green and blue. The constraint we have given is such that no two adjacent regions should have the same colors, like WA and NT should not have the same color. And we also saw a solution towards this problem in the last class, where we have Western Australia and Northern Territory having red and green. Similarly, these two territories, where Northern Territory and Queensland having green and red, and South Australia and New South Wales having different colors. So, this constraint is satisfied according to this map. Now, given the problem of x, d and constraint, how are we going to achieve this solution? So, that solution basically we are going to deal with the backtracking search. Again, last time we saw this algorithm, where the function here is going to be backtrack search, and this is a recursive type algorithm, where if you see this backtrack assignment.csp, and here this backtrack is being called again basically. And one of the examples we saw again here is having the 4 blocks A, B, C and D, where the two adjacent regions should not have the same color. So, according to that algorithm, we pick up any two adjacent regions. Suppose we pick up A and B here, and here it is valid assignment because that constraint is obeyed. The constraint is no two adjacent regions. So, initially there is no that constraint is satisfied. So, it picks up. Now, when we go back here, A and B, suppose we give B as a color red to this, then there is a conflict in the constraint in the assignment, where the constraint is not being obeyed. So, it has to backtrack, and this backtrack occurs due to the recursive nature of it, and then it assigns color B for B it is green. So, here it is obeyed. So, this is how this backtracking is occurring. Now, what are the points, key points of this backtracking search? The first one, it is simple. Okay, it is just like a depth first search. We go and we have backtracks and finds the solution, but it is very slow, especially when the problem size is very large. Maybe if the nodes are in the order of 1000 or 10,000, is going to be slow, or in millions. And the better aspect of it is, if it is earlier, it can detect the failure early because of the backtracking nature. But the search space is going to be n factorial d power n, which is very huge. It is exponential. And now, how to reduce this? We can use some kind of heuristics, and that heuristics we can call it as a minimum remaining values or least constraining value, which we will be seeing in the next few slides. And this we will be combining with another method called forward checking, and other method is going to be constraint propagation. through these methods we can reduce the search space and we can get the solution a bit faster. So, in the next few slides we will be looking at few of these algorithms. The first one would be the forward checking along with the minimum remaining value. Let us assume one example here, a simple example. Here we have taken 4 nodes. If you see, I have just put as a graph with assume these are going to be some kind of a city. So, A is adjacent to B and B is adjacent to D and B is adjacent to C. So, initially what we will be doing is, and again it is the same example where no 2 adjacent regions should share the same color. So, instead of Australian map, I have taken a simple example of 4 cities where A is adjacent to B and B to C, A to C and C to D. Now, for all the 4 regions or here it is going to be the nodes and the constraints are going to be the edges. Again, nodes are going to be the region and constraint are the edges. Nodes are regions or the variables. Okay. Suppose we say A, initially we are going to assign all the domain values to this variable. Suppose A will have all red, blue and green we are assigning, B also will have all the 3 colors that are being assigned, C also will have the 3 colors and D also have the 3 colors. Now, in step 1 we are assigning A to be red, and when we are assigning A to be red, the immediate next neighbor B and C will not be red. Therefore, we can remove that from this variable, the value from this variable where B cannot be red and C cannot be red. That leaves us with B as blue and green and C as blue and green and D has all the 3 colors. And the value that is remaining is going to be the minimum remaining values. This is the heuristic that we are mentioning here. So, once we assign A, B's domain value is getting restricted to blue and green and similarly C's domain value is restricted to blue and green here. Now, in the next step, suppose we assign blue to B, then red already has is assigned to A and blue is assigned to B, which means C cannot be blue and D also cannot be blue. So, the remaining value, minimum remaining value for C is green and minimum remaining value for D is red and green. So, through this way, in this case, in the next step, suppose if C automatically gets assigned as green, in this case D would be red again through the minimum remaining value, which is after blue and green it is going to be red. So, through this method we can assign for each of the values in the variable, it can be assigned properly such that no 2 adjacent regions are sharing the same color. So, this is one example of using minimum remaining value with the forward checking method. Forward checking, why it is called forward checking is because at the first instance we are assigning all the values to the domain and then using minimum remaining we are reducing one by one. The next heuristic is the degree heuristics. Again, this is an example of map and Romania. This is taken from chapter 6 of Russell and Norvig, where if you see, we have also seen this in the last time's class, where if you see this map of Australia, if we convert that to a graph, this is a conversion of that to a graph. Here each of the region is going to be a node, the variable is a node, the edges are going to be the constraint. And if we see W A and N T are connected, these are adjacent regions, and W A is connected to S A, it is the adjacent region. And this heuristics, the degree heuristic says wherever the most degree is occurring, we can color it first. And if we check the degree of this graph, for W A it is going to be 1 and 2, for S A it is going to be 1, 2, 3, 4 and 5. So, if we look at this graph, S A is connected to 5 different regions. So, if we are able to color this first as red and then color this as blue, and red and blue cannot be the same here. So, we can color as green, and here if it is going to be green red, this can be colored as blue, and if red and blue, this can be colored as green and this can be blue. This can take any color which is green. So, if we see blue, green, red, then red, green, blue, then red, green, blue and red, blue, green. So, note using this heuristics we can this is the maximum degree of heuristic. So, using this metric or this heuristic, we can address the constraint such that no two adjacent regions can share the same color. So, this is the second type of heuristic. Now, how do we map the consistency? Consistency using the node. There are basically two types. One is the node consistency, another one is the arc consistency. And why this consistency is required is, suppose we have a search tree where we have one node and that consistency should be propagated to the other node. Suppose we say have a node having say domain value, assume that D A is equal to 5, 6, 7, 8, and if I say D A should be greater than 7, then at this after considering this metric or this constraint, this value should be only 8, and after this also it should be only 8. So, even after several things, the same value should remain, the consistency should be applied, the same consistency with respect to that constraint should be satisfied. This we call it as the consistent, the normal colloquial language where we have the consistency method. The same holds good for AI also. Now, there are two types I said that earlier, which is the node consistency and the arc consistency. A node consistency is the example that I gave. Suppose x is equal to 1, 2, 3, here I gave 5, 6, 7, 8. Suppose it is going to be 1, 2, 3, and if I say it is going to be greater than 1, then x should be equal to 2, 3. The other one is the arc consistency. Arc here represents the constraint. So, how is it going to get propagated? How can we maintain that consistency? It is through the famous algorithm called AC3 algorithm, and that we will see in the next slide. And the third level is the path consistency. Path consistency is there are 3 nodes or 3 variables where we have x, y and z, and if I have x is consistent with y and y is consistent with z, can x be consistent with y or x be consistent with z? Okay. Since x is consistent with y, x will also be consistent with z. This is called as a path consistency, and this can be maintained using the graph which I have shown earlier for the Australian map. Now, we will go ahead with the second algorithm, which is the AC3 algorithm. Okay. So, if we will first look at this algorithm, then we will solve a problem with this algorithm, then come back again to this algorithm and see. Okay. So, it goes like this. The algorithm begins here and I is a variable which goes from 1 to p. Here p is going to indicate the number of nodes in the CSP problem. Q is basically a queue that we maintain for the constraint, and remember this arc of G is a graph. G is a graph, and I j, it is an arc from one node to the other, which basically means the constraint. When q is not going to be empty, then we will do these two steps. The steps are, you delete any arc from q first and revise it. We will see how it revised. How is it getting revised is because we are going to apply the constraint one by one, and once we apply the constraint, the value of node will get changed, and once the node will get changed, we will revise this q, the q earlier, and if we are able to get this q again and again, we will revise this arc into this q, and at one point of time this q will be empty, and when it is empty we will come back out of this algorithm, and when it is empty the solution is obtained. At the first instance, it may look intimidating and it may not be clear. We will do this example and then we will revisit that algorithm later. Okay. Let us see a very simple algorithm here. Here I have three variables with the domain values 4, 5, 6, 7 for x. The variables here are x, y and z. For x it is going to be 4, 5, 6, 7, for y it is 4, 5, 6, 8, 9 and z it is going to be 3, 5, 6, 9. The constraints that we have kept are x is equal to y and y is equal to z. These constraints are mapped into this graph. This is a graph for this constraint, x is equal to y, y is equal to see here we have an arrow, a double edged arrow. If it is going to be x is equal to y, we have a single edged arrow, and if it is y is equal to x, we have a double edged arrow. And similarly, y equal to z, we have y is equal to z, a single edged arrow and then a double edged arrow. So, when we write as an arc, we have to write this as x comma y as x is equal to y, y comma x as y is equal to x. And similarly, for y is equal to z, this represents x is equal to y, and for y is equal to z, we have to write it as y comma z and z comma y. This is indicating this part, and this is indicating this part. Now, at the initial instance, this is what we have in this queue. Suppose this is the algorithm that we have. Q is, this is a queue that we are maintaining the list of arcs, arc of G. So, this list of arcs we are maintaining as x y, y x. This is because of this constraint, x is equal to y, and this is because of y is equal to z. This is the initial value. In step 1, we are going to delete the first one x y. Deleting in the sense, apply the first constraint x is equal to y. When we apply x is equal to y, x is equal to 4, 5, 6, 7 and y is equal to 4, 5, 6, 8, 9. If we apply x is equal to 1, 4, 5, 6 and dy is also 4, 5, 6. So, dx becomes 4, 5, 6, we are applying only x is equal to 6. So, there is going to be a change only in x and not y. Only when we apply y is equal to x, this will change, y will change. Okay. So, now at this point there is a change in x. So, the idea is wherever there is a change in x, bring back the arc anything incident on which there is, where there is a change. Here there is change in x. So, wherever there is an incident on x, bring it. So, change in x, the incident on is y x. So, therefore, bring it, but it is already there in this queue, y x is there. So, we need not bring it again. This queue becomes, because we have deleted x y, this queue is become y x, y z and z y. So, at the end of first step, we have this queue. So, this was the reference arc constraint which is carried over from the previous slide. So, after first step, our queue becomes this value. Now, in the second step, we delete the first one which is y x, and when we have, remember we had x value as 4, 5, 6, y value 4, 5, 6, 8, 9 here. When we apply y is equal to x, then whatever value in y, if it is equal to x, that will be taken. So, in this case x is equal to 4, 5, 6 and y is equal to 4, 5, 6. Z is no change, which means there is an update in y, there is a change in y. So, whatever is incident on y, bring it back. So, what is incident on y is going to be x y and z y from this Q. So, whatever there is an incident, that we have to bring it back. Now, in this Q we already have z y, but x y is not there. So, we have to bring it back. So, we are bringing it x y here. So, this is the end of second step. Now, at the end of second step we have y z, z y and x y. So, after second step we have y z, z y and x y. Now, the same procedure we delete the first, always remember in Q we are going to delete one from the first in first out. So, whichever is first, which is y z, this y z is getting deleted here, and this means this apply y equal to z. So, remember we had x as 4, 5, 6, y as 4, 5, 6 and z as 3, 5, 6, 9. When we apply y is equal to z, these two values 5, 6 in y and z 5, 6 in y, these two are going to be equal. Therefore, y gets changed to 5 and 6, dz is no change. There is a change in y. So, again whatever there is an incident on y should be brought back. So, if we look at Q, x y, the y is incident because of this arc x y and there is another one z y. But according to this Q, z y and x y is already there, therefore, nothing to be changed. So, our Q gets reduced to z y and x y. So, after step 3 this is going to be the result z y and x y. Now, after step 3 we have this result. In the first Q, z y is there. So, we will delete the z y, that will result in 4, 5, 6, x will be the same as 4, 5, 6, we have not touched x y. Now, y is 5, 6 and z is 5, 6, z gets changed, z earlier it was 3, 5, 6, 9, now z gets changed, there is a change in z. So, whatever incident on it, bring it back. So, y z should be added in Q. So, that is added here. So, this becomes x y and y z is added. So, this becomes y z. So, Q will now have x y and y z. Now, the first one that is there in the Q is x y. So, delete x y, which means apply x is equal to y. Remember, we are doing this second time. So, where this x earlier it was 4, 5, 6, after say previously x was 4, 5, 6 and y was 5, 6, and when we apply x is equal to y, this 4, 5, 6 will be equal to this. So, x changes 5, 6. Now, what is incident on x? It is y x, this should be brought back, bring back y x. So, our Q becomes y z and after this y x. And if you notice, at this point in time we have the solution already, x is equal to 5 6, y is equal to 5 6 and z is equal to 5 6, where this constraint is getting satisfied when we apply to all the 3 domains. So, after step 5 we have the 2 variables y z and y x, and delete y z, we will achieve the same value, there is no change, because at this time all the 3 are going to be equal. So, now after this deletion we have only y x, and in the next step when we delete y x, Q becomes nothing, that is empty in Q. which means until this point the algorithm gets repeated and then at this point the algorithm comes out of it. At this stage if you see x is equal to 5 6 which is equal to y and z. So, at this point the solution is obtained. Now, if we revisit back that algorithm, we started off with I is equal to 1 to p, p is going to be the number of nodes. In our case in the previous example we have 3 nodes as x, y and z. Q is the queue that we had with x, y, y, z and other arcs here. When q is not equal to empty, we selected one of the arc. Remember we deleted the first arc from q and then revised it in the sense wherever the arc is incident we brought it back and we deleted again and again until the constraint gets satisfied. So, this is the essence of arc propagation algorithm or AC3 algorithm. Now, so we have seen the constraint satisfaction problem, one of the solution through AC3 algorithm. Now, there are a couple of questions on the constraint satisfaction problem. The first question would be the define domains, variables and constraints for this specific problem. Okay. A university needs to schedule 3 classes math, physics and chemistry in 3 available slot 1, 2 and 3. These are the conditions must be met. There are 2 conditions. No 2 classes can be scheduled in the same time slot, like just like any college slot you would be aware of. The physics class cannot be scheduled in slot 1. So, you can have some node consistency type of thing. So, for these tasks, okay, identify, the first problem is simple, identify variable, domains and constraint for this constraint satisfaction problem. The second task would be represent the problem using these 3 components. Okay. So, this is the first question. The second question is solve using a CSP, again using AC3. We have 3 variables x, y and z just like what we solved now, with d of x as 1 2 3, y as 2 3 and z as 1 3, with the following constraint: x is not equal to y, y not equal to z and x greater than z. For this apply constraint satisfaction problem like AC3 algorithm, and after AC3 algorithm see how the domain value is getting fixed. So, these 2 questions can be solved using the CSP problem. Now, what we have seen as a summary of this module, we have seen in this module we have seen the CSP overview that was defined with variables, domains and constraint. The domains are going to be in the form of, say, if we take the example of Australian map, the regions, or if in the case of the other one like the puzzle, it can be some kind of variables there also, and the domain or the values assigned from the domain to the variables, it should be such that the constraint should be satisfied. And to solve, we have seen the backtracking method, but since the backtracking method it is exponential, the search space is exponential, the time will also go exponential. We have seen some methods using heuristic, one is the forward checking, another one is the degree heuristic and other constraint propagation methods like AC3 algorithms. I have also given 2 problems which is to be solved, and we will see it in the next session. The next course module we will be seeing on the adversarial search.